Imagine waking up one morning and seeing a sunrise that does not look like a sunrise anymore. Not a bright disk rising over the horizon. Not the familiar sun, small enough to hide behind your thumb. Not the warm yellow light that has shaped every day in human history. Instead, the entire sky ahead of you begins to glow red. The horizon burns before the star itself appears. Clouds turn copper. Oceans reflect a dull orange light. Shadows stretch in strange directions, not because the star is small and sharp, but because it is huge, bloated, unstable, and almost impossible for your mind to place at a normal distance. Then you realize the terrifying part. This is not a bigger sun. This is a star so enormous that if Earth orbited it the wrong way, Earth would not simply be warmed by it. Earth could be inside it. Before we begin, if you enjoy calm journeys through space, take a second to subscribe, like the video, and write a comment telling us where you are watching from and what time it is where you are right now. It is always strange to remember that while we are exploring the universe together, someone may be listening at midnight, someone else may be watching at sunrise, and someone else may be falling asleep under a completely different sky. Tonight, you are watching the Just About Space channel, talking about what would happen if Earth orbited the biggest star ever found. And to understand that question, we first have to be careful with the word biggest. Because in astronomy, the biggest star is not always the most massive star. It is not always the brightest star. It is not always the hottest star. A star can be enormous in size, but surprisingly thin and cool at its outer layers. Another star can be smaller in radius, but far more massive, burning with a violence that makes it one of the most powerful objects ever observed. So when people ask about the biggest star ever found, they are usually talking about radius. How wide the star is, how much space its surface would occupy if you placed it at the center of our solar system. That is where the names become strange. UY Scuti, Stevenson 218, VY Canis Majoris, Westerland 126, NML Cygni. These are not normal stars. They are not gentle suns waiting quietly in space. They are red supergiants or possible red hypergiants, stars that have expanded into giant unstable envelopes after burning through earlier stages of their lives. Some estimates place their radii hundreds or even more than 1,000 times larger than the radius of our Sun. Some values are uncertain because these stars are far away, dusty, variable, and difficult to measure with clean edges. That is important. A star like the Sun has a surface we can speak about with confidence, even though it is made of plasma. A red supergiant is different. Its outer atmosphere can be extended, turbulent, full of gas and dust, and changing with time. Its apparent size depends on wavelength, model, distance, and the way astronomers define the outer boundary. So this video is not going to pretend there is one perfectly settled champion with a neat number attached to it. Instead, we are going to imagine Earth orbiting one of the largest known red supergiant candidates, a star so huge that its radius might be measured in astronomical units. An astronomical unit, or AU, is the average distance between Earth and the Sun, about 150 million kilometers. Earth orbits the Sun at 1 AU. Jupiter orbits at about 5.2 AU. Saturn is about 9.5 AU plus 2 AU from the Sun. Now think about that slowly. Some of the largest star candidates are not just bigger than the Sun by a little. Their outer layers could extend several AU from their center. That means, if you placed one of these stars where the Sun is, its visible or semi-visible outer atmosphere could reach beyond the orbit of Mars, and in extreme estimates perhaps toward or beyond the region where the asteroid belt begins. Earth at 1 AU would not be orbiting safely outside the star, it would be buried inside the star's expanded atmosphere. And that is the first answer to the question. If Earth orbited the biggest star ever found at the same distance we orbit the Sun, Earth would not survive as a planet in any recognizable way. There would be no blue sky, no oceans, no cities, no forests, no quiet morning air. There would be no humans standing on the surface looking up at an enormous red disk, because the surface itself would already be gone. The star would engulf Earth, not like a flame swallowing a piece of paper in one neat instant, but like a planet being dragged into a vast, hot, diffuse, moving envelope of plasma. The word plasma matters here. A star is not fire in the ordinary sense. Fire needs chemistry. It needs oxygen reacting with fuel. A star shines because its core is powered by nuclear fusion, and because energy travels outward through layers of ionized gas. Near the outer layers of a red supergiant, the gas can be cooler than the surface of the Sun, but cooler does not mean safe. It is still a stellar environment, still far beyond anything Earth's atmosphere, oceans, rocks, or life could handle. Before Earth ever reached anything like a solid surface, it would be heated, stripped, and broken apart. The atmosphere would be the first obvious casualty. Earth's air exists because gravity holds it close, and because the energy arriving from the Sun is within a range that allows a stable climate. Around a giant star, the energy balance would collapse. The upper atmosphere would expand. Molecules would escape more easily, and intense radiation and stellar wind would batter the planet. If Earth were actually inside the swollen outer atmosphere, the situation would be worse than simple overheating. The planet would be moving through gas, thin compared to air at sea level, perhaps, but enormously hot and extended compared to the vacuum Earth normally travels through. That gas would create drag. Drag would steal orbital energy. The planet's orbit would shrink. Earth would spiral inward. As it moved deeper, the surrounding gas would become denser and hotter. Friction would heat the planet further. The star's gravity would dominate everything. Earth's crust would not remain stable. The oceans would boil away. Rocks would melt. The atmosphere would become a temporary expanding cloud. Eventually, Earth would no longer be Earth. It would become material, a small contribution to the outer layers of a dying giant star. That image is terrifying because it reverses the way we usually think about planets. We imagine planets orbiting stars from a safe distance, like tiny companions around a central light. But around a red supergiant, a planet too close is not a companion. It is fuel for the story of the star's final life. And yet, that is only the simplest version of the thought experiment. Because a careful viewer might ask something smarter. What if Earth did not orbit at 1 AU? What if Earth were moved far enough away? Could there be a safe orbit around the biggest star ever found? Could Earth survive if it stayed outside the star's huge body? Could there be a zone where the light is not instantly fatal, where oceans do not vanish at once, where the sky is strange but not immediately deadly? That question takes us into the habitable zone. The habitable zone is the distance from a star where liquid water could exist on the surface of a planet, assuming the planet has the right kind of atmosphere. It is sometimes called the Goldilocks zone. Not too hot, not too cold. Earth sits in the Sun's habitable zone, but the habitable zone is not fixed. It depends on the brightness of the star. A star that is dimmer than the Sun has a habitable zone closer in. A small red dwarf may have planets orbiting very close, much closer than Mercury orbits the Sun, and still receive Earth-like warmth. A star that is much brighter than the Sun pushes its habitable zone far outward. The basic idea follows the inverse square law. Light spreads out as it travels. If you move twice as far from a star, you receive 1/4 as much energy. If you move 10 times farther, you receive 1/100th as much energy. So, if a star is 100,000 times more luminous than the Sun, a planet would need to be roughly the square root of 100,000 times farther away to receive similar energy. The square root of 100,000 is about 316. So if a red supergiant shines with around 100,000 times the Sun's luminosity, an Earth-like orbit in terms of incoming energy might not be 1 AU. It might be hundreds of AU away. That is not a small adjustment. That is far beyond Neptune. Neptune orbits about 30 AU from the Sun. Pluto's distance varies, but it is often around 30 to 50 AU. The Kuiper Belt stretches through the icy outer solar system. A habitable zone around an enormous luminous star could be hundreds of AU out, in a region that would feel like the remote outskirts of our own planetary system. Now imagine Earth there. Not 1 AU from the giant star. Not inside the star. Not close enough for the oceans to flash into vapor immediately. Instead, Earth has been placed hundreds of AU away, at a distance where the total energy arriving at the top of the atmosphere might be roughly similar to what Earth receives from the Sun today. At first, that sounds like a solution. Same energy means same climate. Right. Not exactly. Because stars do not only differ in brightness, they differ in color, temperature, stability, lifetime, radiation, wind, and the way their light interacts with atmospheres and surfaces. A red supergiant is cooler at its visible surface than the Sun. Its light is redder, richer in longer wavelengths, with less blue light compared to our daylight. The sky on Earth, if the atmosphere survived and remained similar, would not look exactly like our sky. Sunlight scatters strongly at shorter wavelengths, which is why our sky is blue. A redder star would change the color balance. Sunrise, noon, and sunset would all feel alien. The star itself would also appear enormous. This is one of the strangest parts of the thought experiment. If the star has a radius of several AU, and Earth orbits hundreds of AU away, the star might still look much larger in the sky than the Sun does from Earth. Our Sun appears about half a degree wide in the sky. A red supergiant with a radius of, say, 5 AU viewed from 300 AU away would have an angular diameter of nearly 2 degrees, perhaps several times wider than the Sun appears to us. If the radius were larger or the habitable distance different, the apparent size could change. But the idea remains. The star would not look like a small, sharp disk. It would look like a huge red presence, a swollen ember hanging in the sky. Even from hundreds of AU away, the star's size would be obvious. And because the star is cooler and more diffuse, its edge might not look crisp. It could appear softened by extended atmosphere, dust, and outflowing gas. The light might feel less like the hard sunlight of a clear noon and more like the glow of a vast furnace seen through a cosmic haze. But the energy could still be enough to warm the planet. That is where the beauty and the danger overlap. You could imagine an ocean under red daylight, clouds lit by a star larger than anything humans have ever seen in our sky. A world where shadows are softer because the light source is wider. A world where every sunrise is slower and stranger because the star is not a point of light, but a giant sphere. Yet this environment would not be peaceful. The biggest stars are not long-term homes. They are temporary monuments to stellar instability. A star, like our Sun, can remain stable on the main sequence for about 10 billion years. It gives planets time. Time for chemistry, time for oceans, time for evolution, time for life to make mistakes, recover, diversify, and build complexity. Very massive stars do not offer that kind of patience. The most massive stars burn through their nuclear fuel quickly, living for only millions of years. Red supergiants are later life stages of massive stars. They may already be close, on astronomical timescales, to dramatic endings. Even if Earth could be placed at the right distance for comfortable temperatures, the question becomes, comfortable for how long? 1,000 years? 1,000,000 years? A few million? For life, those numbers are not equal. Human civilization has existed for only a tiny fraction of Earth's history. Complex life took billions of years to appear. Multicellular organisms, animals, forests, and intelligent observers were not produced quickly. Earth needed long stability, not just temporary warmth. Around the largest stars, a planet may receive energy, but not time. And time is one of the hidden ingredients of habitability. This is why the thought experiment becomes darker the deeper we go. The biggest star is not terrifying only because it is large. It is terrifying because size is connected to violence, instability, and short cosmic life. A star that huge is not a calm parent. It is a dying giant. It may be losing mass through powerful stellar winds. It may be pulsating, swelling, and shrinking over time. It may be shedding gas and dust into space. Its brightness may vary. Its outer layers may be uneven, turbulent, and convective on scales larger than planets. The star might have giant cells on its surface, enormous regions of rising and falling plasma. On the Sun, convection creates granules, patterns of hot material rising and cooler material sinking. But on a red supergiant, convective structures can be immense, with cells that might be a significant fraction of the star's radius. Try to imagine weather on a star where a single moving region of plasma could be larger than Earth's entire orbit around the Sun. That is the scale involved. Now place Earth in orbit around it. Even far away, Earth would not simply receive steady, predictable sunlight. It might receive a changing flood of red and infrared radiation. There could be variations as the star pulsates. There could be dust episodes when the star sheds material and partially dims itself. There could be powerful winds carrying gas outward. There could be changes in luminosity that shift the climate over time. A planet's climate does not like sudden changes. Earth's climate is complex, with oceans, clouds, ice, carbon dioxide, water vapor, and life all connected in feedback loops. Small changes can build over long periods. Large changes can push systems into new states. Around a red supergiant, the energy source itself may not be reliable enough for a delicate biosphere. If Earth received too much light for a few centuries, oceans could warm, water vapor could increase, greenhouse feedbacks could strengthen. If the star dimmed behind dust or changed output, glaciers might spread. The atmosphere would constantly adjust to a star that is not offering the same kind of stable energy our Sun has provided for billions of years. This is one reason the Sun is more special than it looks. It is not the biggest star. It is not the brightest. It is not the most dramatic. But it is stable enough, and for life, stable enough may matter more than spectacular. The biggest star ever found might impress us from a distance, but it would be a terrible star to call home. Still, let us stay with the thought experiment. Let us imagine Earth has been moved to the right orbit. The star is enormous, red, and far away. The planet receives roughly Earth-like energy. What would a day feel like? The first difference might be the sky. A red supergiant's light is cooler in color temperature than sunlight. Human eyes would adapt, but the world would look different. Blue objects might appear muted. Reds and oranges might feel stronger. Shadows would be less sharp if the star's apparent disk were large enough. The atmosphere's scattering would still create color, but the balance would shift. Plants, if they existed or were transported from Earth, would face a different spectrum. Photosynthesis on Earth uses visible light, especially blue and red wavelengths. A redder star could still provide usable energy, but ecosystems might adapt differently. Leaves might not be green in the same way. Organisms could evolve pigments tuned to the available light. A world under a red giant might develop a darker, more infrared-sensitive biosphere if life had enough time to adapt. But in our scenario, Earth is not evolving from scratch. Earth is being moved, so existing life would be shocked. Plants adapted to solar daylight would experience a new spectral environment. Temperatures might be adjusted by distance, but light quality would change. Seasonal cycles would change if the orbit were different. Day length could remain the same if Earth kept its rotation, but the brightness and color of each day would feel unfamiliar. The Moon would still orbit Earth, unless the move disrupted it. Tides would continue, but the night sky would be transformed. Because around a giant star, night might not feel like night in the same way. If Earth's orbit is far enough away, and if the planet still rotates once every 24 hours, the star would set below the horizon. But its enormous angular size could make sunrise and sunset longer. The star's extended light could make the transition between day and night less abrupt. And if the system were filled with dust from the red supergiant's mass loss, that dust could reflect and scatter light across the system. The sky might have a faint reddish glow even when the star is below the horizon, depending on the density and distribution of material. The night could be haunted by the star even after it sets. This sounds beautiful. But beauty is not safety, because the same dusty, glowing environment tells us the star is losing itself. Red supergiants do not keep their outer layers forever. They can drive powerful stellar winds, sending material into space. Over time, this changes the star's mass. Changing mass affects planetary orbits. If a star loses mass, its gravitational grip weakens, and planets can drift outward into wider orbits. In our solar system, when the Sun becomes a red giant in the far future, it will lose mass, and the outer planets will gradually move outward. Around a more massive giant star, the effect could be stronger and faster. An Earth-like planet around such a star would not simply orbit a fixed central object. It would orbit something that is evolving. The year could change. The amount of light could change. The gravitational architecture of the system could shift. And if the star has companion stars, as many massive stars do, the situation becomes even more complex. Massive stars often form in clusters or multiple systems. Nearby stars can perturb planets, strip material, or bathe worlds in additional radiation. A planet in such a system would live in a neighborhood very different from our relatively quiet solar environment. The Sun is alone. That loneliness may be part of why Earth has had a stable history. Around the biggest stars, solitude is not guaranteed. They are born in crowded nurseries among other massive stars, intense radiation fields, and turbulent gas. A planet trying to form and survive there would face chaos from the beginning. This brings us to another important question. Could Earth even form around the biggest star? If we are imagining Earth being magically placed there, yes, we can explore the consequences. But if we ask whether an Earth-like planet could naturally form around a giant star that later becomes one of the largest red supergiants, the answer becomes more difficult. Massive stars live fast. Planet formation takes time. Dust grains stick together. Pebbles become planetesimals. Planetesimals collide and grow into planetary embryos. Gas giants gather envelopes before the disk disperses. Rocky planets continue colliding and clearing their orbits over tens of millions of years. But very massive stars can disrupt their own planet-forming disks with strong radiation and winds. They also evolve quickly. By the time a stable rocky world might finish assembling, the star could already be moving toward dangerous phases. This is one reason we do not usually look for Earth-like life around the most massive stars. They are bright, dramatic, and scientifically important, but not ideal homes. Life does not only need energy, it needs a stable platform. It needs chemistry protected from constant disaster. It needs enough time for small changes to accumulate. It needs a star that does not rush through its life like a burning fuse, a huge star is more like a cosmic emergency than a cosmic hearth. Still, let us continue with Earth already in place. Let us ask what happens at the level of physics. At a safe distance, Earth receives similar total energy. The temperature might be manageable. But the star's gravity is stronger than the sun's, if the star has much greater mass. This changes orbital speed. A planet's orbital period depends on its distance and the mass of the star. Farther orbits are slower, but higher stellar mass pulls harder. Around a massive star, an orbit hundreds of AU away could still take a long time, perhaps hundreds or thousands of Earth years, depending on exact mass and distance. That means seasons would change completely. Earth's seasons are caused by axial tilt, as we orbit the Sun once per year. If Earth orbited a red supergiant at hundreds of AU with a period of centuries, each season might last decades or longer, assuming the axial tilt remained similar. Imagine a spring that lasts 50 years, a summer that stretches across generations, a winter that children are born into and their grandchildren may still remember. Climate systems would respond in strange ways. Ice sheets could grow during long winters and melt during long summers. Oceans would store heat. But even oceans have limits. The carbon cycle would operate under an unfamiliar rhythm. Ecosystems would need to survive seasonal timescales far beyond what Earth life evolved for. If human civilization were transported there, agriculture would have to be redesigned. Migration patterns would become planetary-scale planning. Cities might be built for centuries-long climate phases. The meaning of a calendar would collapse. The star would not only change the sky, it would change time. And that may be one of the most haunting consequences. Around a giant star, even if the energy is right, the rhythm of life may be wrong. The year could be too long. The stellar lifetime could be too short. The light could be unstable. The future could be violent. This is why habitability is not a single number. You cannot simply say, same energy, therefore same Earth. A planet is a system inside a system. Change the star, and every part of that system feels it. What would happen if Earth orbited the biggest star ever found? At first, you might think the answer is about size. A bigger sunrise, a larger disk, a more dramatic sky. But the true answer is about impermanence. The largest stars are not just big. They are near the end of an unstable story. They do not provide the quiet billions of years that made Earth possible. They burn through their lives, swell into enormous forms, shed themselves into space, and then leave behind remnants or explosions that reshape everything around them. Earth around such a star would be living beside a countdown, not a human countdown, not years or centuries necessarily, but a cosmic countdown, still far shorter than the slow patience of our sun. And that forces us to look differently at the ordinary star in our own sky. The sun is not impressive by the standards of giant stars. It is not a record holder. It is not large enough to swallow the orbit of Jupiter. It does not dominate a stellar cluster with monstrous winds. It does not glow with millions of times its current brightness. But it has given Earth something more valuable than spectacle: consistency. For billions of years, the sun has changed slowly enough that Earth systems could adapt. It has brightened gradually, not violently. It has produced storms, flares, and cycles, but not the chaos of a massive dying giant. It has stayed in a range where liquid water, atmosphere, geology, and life could maintain a long conversation. That conversation produced oceans, then cells, then oxygen, then animals, then forests. Then, minds capable of wondering what would happen under another star. The biggest star ever found may be more visually astonishing, but the sun is the reason anyone is here to be astonished. Earth remains Earth. Same oceans, Same atmosphere, same moon, same continents, same life. But the Sun disappears from the center of the solar system and is replaced by a red supergiant, so large that its outer layers stretch far beyond the orbit we normally call home. The first problem is geometry. Our planet travels around the Sun at 1 AU. The Sun's radius is only about 0.00465 AU night. That means Earth is more than 200 solar radii away from the Sun's center. There is a huge gap between the solar surface and Earth's orbit. With an extreme red supergiant, that gap can vanish. If the star's radius is several AU, Earth's orbit lies inside the star's atmosphere. This does not mean Earth hits a hard wall. Stars do not have solid surfaces, but it does mean Earth is surrounded by stellar material, moving through gas, plasma, radiation, magnetic fields, and heat. The planet would no longer be in space as we understand it. It would be in a star. At first, the outermost layers might be thin, but even a thin stellar atmosphere is not empty. Earth would plow through it at orbital speed, and the interaction would be violent. Gas would pile up ahead of the planet. Energy would be deposited into the atmosphere and surface. Drag would slow the orbit. The planet would lose altitude in stellar terms. This is similar in concept to a spacecraft re-entering Earth's atmosphere, but on a planetary scale and inside a star. A spacecraft re-entry lasts minutes. Earth's in-spiral might unfold over a longer time, depending on density, orbit, and structure. But the result would not be survival. The atmosphere of Earth would heat and expand. The oceans would begin to evaporate. Water vapor would become a powerful greenhouse gas, trapping more heat and accelerating the damage. Clouds would not save the planet. The thermal forcing would be far beyond natural climate variation. As temperatures climbed, the surface would transform. Ice would vanish first. Then forests would die. Then soils would dry. Then oceans would boil. The pressure of steam in the atmosphere would rise. Ultraviolet radiation and heat would split water molecules. Hydrogen could escape. Oxygen could react with surface minerals or remain temporarily in the atmosphere before being lost or transformed. Earth's blue appearance would fade. From a distance, if anything could watch, the planet might first turn white with cloud, then brown and gray, then glowing and molten. But inside the star, there may be no distant view. Earth would be hidden in the envelope. The moon would not remain safe either. The moon orbits Earth at about 384,000 kilometers, tiny compared with the scale of a giant star. It would be dragged into the same environment. Its surface would heat. Its orbit around Earth could be disturbed by tidal forces, drag, and mass loss. Eventually, the Earth-Moon system would be torn from its familiar balance. The story of tides, eclipses, and lunar phases would end. No one would watch the moon cross the face of the giant star. There would be no one left. This version is not a slow survival story. It is planetary destruction. But the reason we spend time on it is that it reveals something essential about scale. The distance between Earth and the Sun feels enormous to us. Light takes about 8 minutes to cross it. Human spacecraft take months to reach Mars, years to reach outer planets, and decades to enter interstellar space. But compared with the largest stars, 1 AU is not a majestic distance. It is close, very close. It can be inside the star itself. The solar system teaches us one sense of scale. Giant stars teach another. Now, move Earth outward. Let us give the planet a chance. Suppose the red supergiant is 100,000 times brighter than the Sun. This is not a fixed number for every candidate, but it is a useful order of magnitude for an enormous luminous star. To receive roughly the same total energy Earth receives from the Sun, Earth would need to orbit around 316 AU Lay, where that is more than 10 times Neptune's distance. From our solar system's point of view, Earth would be moved into the deep outer darkness, but around the giant star, that distant orbit could feel warm. This is the strange power of luminosity. A star can be so bright that the region of Earth-like heating is pushed into what would normally be a frozen realm. At 316 AU from the Sun, Earth would be unimaginably cold. Sunlight there would be roughly 100,000 times weaker than it is here. The oceans would freeze. The atmosphere might collapse over time. Solar energy would barely matter. But at 316 AUA from a star 100,000 times brighter than the Sun, the total energy could be similar. Same distance from warmth in a sense. Different star, different system. If Earth were placed there, the first surprise would be that the giant star might still dominate the sky. It would not be a tiny point. It would not look like the Sun seen from Pluto, because even though the planet is far away, the star itself is physically enormous. A large angular size changes how light behaves on the surface. On Earth, sunlight arrives from a disk about half a degree wide. Shadows can be sharp because the Sun's apparent size is relatively small. Around a larger apparent star, shadows soften. Edges blur. More light reaches around objects from slightly different angles. The world might feel as if it is illuminated by a glowing wall rather than a small lamp. Artists sometimes imagine alien planets with giant suns filling the sky. Usually, that would mean the planet is too close and too hot. But around a red supergiant, a large apparent disk could happen even at a far cooler orbit, because the star is so physically huge. The daytime sky would be unsettling, not necessarily brighter than Earth's noon, if the energy is balanced, but visually different. The star would be a red-orange disk several times wider than the Sun. It could have darker patches, brighter regions, haze, and perhaps changes over time. It might look less like a clean circle and more like a turbulent, living furnace. Its surface temperature would be lower than the Sun's, perhaps around a few thousand Kelvin rather than nearly 5,800 Kelvin. That cooler temperature gives red supergiants their color. They are huge not because they are hotter, but because their outer layers have expanded enormously. This is another counterintuitive point. The biggest stars by radius can have cooler surfaces than the Sun. They are luminous because surface area matters. A cooler square meter emits less energy than a hotter square meter. But when the star has millions of times more surface area, the total energy output becomes immense. That is how a star can look red and still overpower a solar system. Now think about Earth's climate. If the incoming energy matches modern sunlight, average temperatures might seem possible, but the spectral shift changes atmospheric absorption. More infrared-rich light interacts differently with water vapor, clouds, and greenhouse gases. Climate models would be needed to know exact outcomes, and they would depend on the star's spectrum and Earth's atmospheric composition. Some infrared light can be absorbed more strongly by gases before reaching the ground. Some wavelengths may heat the atmosphere differently. Cloud feedbacks might change. Ice and ocean albedo could behave differently under redder light than under solar light. Plant life would face changes in photosynthetically useful radiation. A stable climate is possible in principle, but it is not guaranteed by equal total flux. Equal energy is only the beginning. The planet's rotation also matters. If Earth kept its 24-hour spin, day and night would continue, but the year, at hundreds of AU, could be extremely long. The seasons would be slow. Even if Earth kept the same axial tilt, this could produce decades-long transitions. Human life would fit inside a fraction of a season. The poles would have strange histories. If axial tilt remains, polar regions could spend long intervals angled toward or away from the star over portions of the vast orbit. Ice sheets might advance and retreat on timescales that feel geological to people living there. Civilizations would not plan for winter as a yearly problem. They would inherit climate errors. The word year would lose its emotional meaning. Birthdays would no longer track a journey around the star in a familiar way. Most people would never complete one orbit. Generations might pass before Earth returned to the same point in its path. Around such a star, the planet could survive a day, maybe a century, maybe many centuries. But the rhythms that shaped Earth life would be broken, and the sky would always remind you why. A vast red star hanging there, old and swollen, would be a constant sign that the system is temporary. Let us consider gravity more carefully. The biggest stars by radius are not necessarily the most massive at the moment we observe them. Red supergiants may have started with much more mass and lost some of it through winds. Still, many are more massive than the Sun. A planet orbiting a more massive star at hundreds of AU would follow different orbital dynamics than Earth around the Sun. Orbital speed depends on the mass of the star and distance from it. At a large distance, speed is lower. A planet at hundreds of AU moves slowly across its orbit. But if the star is several or many solar masses, its gravity increases the speed somewhat compared with a Sun-like star at the same distance. Even so, orbital periods could be extremely long. A rough example helps. A planet at 316 AUA, around a star of 10 solar masses, would have an orbital period on the order of thousands of years, divided by the square root of the stellar mass compared with the Sun. That still leaves a period far longer than a human lifetime. Exact numbers depend on mass and distance, but the conclusion is clear. This Earth would not have a normal year. That affects more than seasons. It affects the stability of climate cycles, the behavior of ice, the pattern of solar heating across latitudes, and the way societies would measure time. A civilization living there might define time by rotation, lunar cycles, climate phases, or artificial calendars rather than by a completed orbit. But long years are not the only orbital issue. The star itself may be losing mass. When a star loses mass gradually, planetary orbits expand. The planet's year lengthens further. Incoming energy may decline if distance increases, unless the star's luminosity rises at the same time. Around an evolving giant, both luminosity and mass can change. The planet is not orbiting a fixed lamp. It is orbiting an object undergoing stellar old age. This could create moving habitability. The habitable zone may sweep outward as the star brightens and expands, then change again as the star loses mass and evolves. A planet might enter a comfortable zone temporarily and leave it later. Frozen worlds could thaw for a while. Warm worlds could become too hot. Moons and outer planets might experience brief windows of liquid water. NASA has discussed how red giant phases could warm previously frozen worlds around aging stars. In our solar system's future, as the Sun becomes a red giant, distant moons and outer planets could receive more energy than they do today. But such windows are temporary compared with Earth's long main sequence habitability. Temporary habitability may be enough for chemistry. It may not be enough for complex life. This distinction is crucial. A planet can be briefly warm. A planet can have liquid water for a while. But life, especially complex life, may need time measured in hundreds of millions or billions of years. On Earth, life appeared early in geological terms, but complex life took far longer. Intelligence took longer still. Around the biggest stars, time is the missing ocean. There may be light. There may be warmth. There may even be moments of beauty, but the clock is not generous. Now, let us imagine a human observer somehow standing on Earth in this altered system, protected by technology, watching the giant star rise. The first sensation might be silence, not because the world is quiet, but because the scale is too large for the mind to process. The star would not leap over the horizon. It would begin as a glow, then a curved wall of red light. As more of it appeared, the horizon would brighten unevenly. The atmosphere might scatter crimson and amber across the sky. The sunrise could take longer because the disk is larger. The first edge of the star might appear, but the entire star would take more time to clear the horizon. During that interval, the world would be in a strange half-day, lit by an object too big to feel natural. No ancient human myth prepared us for that sky. Our ancestors saw the sun, the moon, planets, comets, eclipses, auroras, and meteors. They imagined gods and omens in the heavens, but they never saw a star that could have swallowed the inner solar system, rising like a burning continent. The sight would be magnificent, and it would be wrong, because a sky like that is not the sky of a safe world. It is the sky of a planet orbiting an aging giant. Every sunrise would carry the future inside it. The star's color would tell you it is cool at the surface. Its size would tell you it has expanded. Its turbulence would tell you it is unstable. Its luminosity would tell you it is powerful. And its evolutionary stage would tell you that whatever stability exists is temporary. This is where the emotional center of the video begins. Earth does not survive because the sun is impressive. Earth survives because the sun is restrained. The biggest star ever found would make our sun look tiny, but it would also make our sun look wise in comparison. Not conscious, not purposeful, but physically suited, by chance and circumstance, to host a world like ours. The sun is not too hot, not too cool, not too massive, not too short-lived, not too unstable. It is ordinary in a way that allowed extraordinary things to happen nearby. A giant star would take that ordinary gift away. Now we need to talk about the surface of a red supergiant. The phrase surface can mislead. On Earth, surfaces are clear: ocean, soil, rock, ice. On the Sun, the visible surface is the photosphere, the layer from which most visible light escapes. On a red supergiant, the photosphere can be extended and complex. Above it, there may be huge atmospheres, molecular layers, dust formation zones, and outflows. The star's outer regions can be so diffuse that defining a clean edge is difficult. This matters for the Earth inside the star scenario, but it also matters visually. The star may not have a sharp limb. It may look fuzzy or irregular. Its brightness may vary across its disk. Huge convective cells may create patterns. Dust can form in outflowing material and partially obscure the star from certain directions. Some red supergiants are variable stars. Their brightness changes over time. They pulse. They breathe. They shed material. From Earth's new orbit, astronomers would monitor the star constantly, not out of curiosity alone, but because every change could matter for climate and survival. A dimming event might cool the planet. A brightening phase might intensify heat. Increased mass loss might change the particle environment. The star would be weather and calendar and apocalypse warning all at once. Imagine weather forecasts that include stellar pulsation, not just clouds over the ocean, not just storms over continents, but the changing output of the star itself. A civilization there would build observatories as life support infrastructure. Stellar astronomy would not be a distant science. It would be practical survival. People would ask, is the star shedding more mass this century? Are dust clouds forming? Has the luminosity shifted? Are winds strengthening? Is the orbit expanding? Are we moving out of the habitable flux zone? Has the core entered a new burning stage? In our world, most people can live their entire lives without knowing what the sun's core is doing. Around a giant star, ignorance would be dangerous. The sky would become a scientific instrument everyone depended on. Now, consider radiation. A cool red supergiant emits much of its radiation at longer wavelengths compared with the Sun. But that does not make it harmless. Total luminosity is enormous. Stellar winds can be powerful. The star may also be part of a complex environment filled with dust, gas, and perhaps companion stars. If the star began as a massive blue or hot star, its earlier life would have been far more hostile. Strong ultraviolet radiation could erode atmospheres and disrupt planet formation. By the time it becomes a red supergiant, conditions may be redder, but the system has already lived through violent earlier phases. So if Earth is placed there only now, we can discuss survival. But if Earth had tried to exist there from the beginning, it would have faced a very different young star. Massive stars are born hot and luminous. They can flood their surroundings with ultraviolet radiation. They can drive winds that sculpt nebulae. They can influence star formation around them. Their environments are not gentle nurseries for small rocky worlds. This is why our thought experiment has a hidden artificiality. Earth is being moved into the system after already forming elsewhere. A natural Earth around such a star is much harder to imagine. But thought experiments are useful because they isolate causes. By moving Earth, we can ask, what does this star do to a planet like ours? And the answer keeps changing depending on distance. At 1 AU, destruction by engulfment. At hundreds of AU, possible temperature balance, but strange climate and unstable future. At even farther distances, perhaps cold survival under a dimmer red giant sky, but not Earth-like comfort. There is no simple safe zone that also offers billions of quiet years. That is the key. This is the version that allows scenes, skies, and survival questions. Let us imagine a distance where the average energy is Earth-like. The planet is still rocky. Oceans remain. The atmosphere is not immediately stripped. The moon remains bound. Human technology works. What happens first? The first problem would be adjustment. Earth's climate is tuned to the Sun's spectrum and its current orbit. Moving the planet instantly would create shocks. The oceans have thermal inertia, meaning they resist rapid temperature changes, but the atmosphere would respond quickly to differences in radiation. Weather patterns would reorganize. Atmospheric circulation depends on where heat enters, how it is absorbed, and how the surface distributes it. If the red star emits more infrared, the vertical temperature structure of the atmosphere could change. The surface might receive different proportions of direct and absorbed energy. Clouds might form differently. Rainfall belts could shift. Deserts could move. Ice margins could retreat or advance. A planet is not a lamp under a bulb. It is a moving machine. Change the bulb, and the machine changes. If Earth's orbit becomes hundreds of AU, the gravitational influence of other planets in the system also matters. If this giant star has its own planets, their orbits may be wide, unstable, or affected by stellar evolution. Earth might not be alone. Large planets could perturb its orbit over time. Comets and debris from outer regions could be destabilized by mass loss, sending impacts inward. Around dying stars, planetary systems can become messy. There is evidence that white dwarfs, the remnants of sun-like stars, sometimes show heavy elements in their atmospheres, suggesting they have accreted rocky debris from disrupted planets or asteroids. Stellar death can shake planetary systems apart. For a planet around an enormous evolved star, the future is not just radiation. It is dynamics. Orbits can change. Debris can move. Moons can be lost. Tides can shift. If Earth's orbit is extremely wide, passing stars and galactic tides become more relevant over very long timescales. Wide orbits are more fragile. In our own solar system, the Oort cloud is loosely bound, vulnerable to passing stars and the Milky Way's gravitational field. A planet, hundreds or thousands of AU from a massive star, may be bound, but the farther out it is, the more exposed it becomes to external perturbations. The habitable zone of a giant star can be so far out that the environment begins to resemble the realm of comets, a warm world in a comet-like region. That is not impossible, but it is strange, and strange systems often have hidden costs. Now consider the star's lifetime in the red supergiant phase. Red supergiant phases are short compared with main sequence lifetimes. A planet warmed during this stage may enjoy a temporary spring after a long frozen history. But the spring does not last billions of years. This idea has been proposed for distant icy worlds around aging stars. When the star expands and brightens, moons or planets that were once frozen could thaw. A world like Europa or Titan, if placed in the right future sunlight, might see surface conditions change dramatically. Ice could melt, atmospheres could expand, chemistry could accelerate. But the window closes. The star keeps evolving. Eventually, it sheds layers, collapses, or transforms, depending on mass. For life, a temporary thaw may be an opportunity, but also a limit. If microbial life already exists under ice, perhaps new warmth could change its environment. But if life has to begin from scratch, the clock may be too short. Abiogenesis, the origin of life, is not fully understood. But complex ecosystems do not appear instantly just because water is liquid. So Earth moved around a giant star. Might remain alive if it arrives with life already present. But a dead planet placed there may not have time to become another Earth. This is an important distinction for the second half of the video, where we will ask not only whether Earth could survive, but whether any world could truly belong to such a star. For now, the answer is becoming clearer. Earth could only survive around the biggest star under carefully chosen conditions. It would need to be far enough away to avoid being swallowed. It would need to receive the right flux. It would need protection from winds and radiation. It would need a stable orbit in a system that may not be stable. It would need climate systems able to adapt to redder light. It would need enough time, and time is the hardest requirement. The largest stars do not give time generously. They burn through it. Now, let us look at the question from another angle. What would the star look like from Earth if Earth orbited at the habitable distance? We already said it might appear much larger than the Sun, but let us slow down and picture it. The star's disk would be wide enough that sunrise begins long before the center appears. The horizon would glow red. The upper atmosphere would brighten in layers. High clouds might catch light first, turning into bands of orange and rust. The ground would remain dim for longer, then slowly fill with diffuse red illumination. When the disk finally rises, it might not look perfectly uniform. It could show mottled brightness. It could appear darker near the edge, depending on limb darkening and atmospheric structure. There might be irregularities caused by outflowing dust or extended gas. It would not look like the sun through a safe solar filter. It would look more like a living surface, seen from far too close, in cosmic terms, even though the planet is actually far away. At noon, the star would dominate the sky, not necessarily blinding in the same color as the sun, but impossible to ignore. Its large apparent size would make shadows soft. Reflections on water would spread wider. Forests, mountains, and buildings would be lit from a larger angle, changing contrast. Human eyes would adapt, but art, architecture, photography, and daily perception would be transformed. Night would bring a different problem. If the system contains dust, the night sky could be filled with faint reflected glow. The giant star's lost material might form a nebula around the system. Over time, outflowing gas could create shells or arcs. Under dark conditions, observers might see structure in the sky not because of distant galaxies, but because their own star is surrounding them with its shed atmosphere. The star would be building its own ghost, and Earth would orbit inside that future ghost. This is poetic, but it is also physical. Mass loss from red supergiants enriches space. Heavy elements created in stars and spread by winds and explosions become ingredients for future generations of stars and planets. The calcium in bones, the iron in blood, the oxygen in water, the silicon in rocks. These elements come from stellar processes across cosmic history. Massive stars are dangerous, but they are also creative. Without them, the universe would lack many of the elements needed for rocky planets and life. So the biggest star is not simply a monster, it is part of the cycle that made worlds like Earth possible. This is why the question becomes complicated. Earth could not safely orbit such a star for long. But Earth exists because earlier generations of massive stars lived and died. The same kind of cosmic violence that would destroy our planet also helped make our planet's ingredients. A red supergiant is both threat and ancestor. If Earth orbited one, it would be in danger. If no stars like it had ever existed, Earth might never have formed. That contradiction will become important later. For now, we stay with the immediate scenario. Let us bring in the difference between radius and mass again, because it matters for the title. The biggest star by radius might be a red hypergiant candidate like Stephenson 2.18, depending on estimates and definitions. But the most massive known stars, like R136A1 in the Large Magellanic Cloud, are different objects. R136A1 is not the largest in radius like a red supergiant. It is extremely massive and luminous, a hot young monster in a dense cluster. If Earth orbited R136, a one at a distance where it received Earth-like energy, the situation would be different from orbiting a cool red supergiant. The star would be much hotter. Its light would contain more ultraviolet radiation. Its stellar wind would be extreme. Its lifetime would be very short. The habitable zone would be far away because of the enormous luminosity, but the radiation environment would still be hostile. An ozone layer, magnetic field, and thick atmosphere might help, but long-term biological stability would be doubtful. So if we ask about the biggest star by radius, we get one kind of nightmare, an enormous red giant envelope. Unstable output, future supernova risk. If we ask about the biggest star by mass or luminosity, we get another kind of nightmare. Intense ultraviolet light, fierce winds, short lifetime, and a violent young environment. Either way, Earth does not get a better home. It gets a lesson. Bigger stars are not better stars for life. They are spectacular, but hostile. The sun's mediocrity becomes precious. But this video is not mainly about fictional civilization, it is about physics. So let us return to what physics says. If Earth orbited too close, engulfment. If Earth orbited at equal energy distance, possible temporary habitability, with major complications. If Earth orbited too far, freezing, unless internal heat or technology helped. If Earth waited for the star to die, catastrophe. That is the framework of the first half. In the second half, we will go further. We will ask what happens to Earth's oceans over time under red giant light. We will examine whether the atmosphere could survive stellar winds. We will imagine the final supernova or collapse. We will compare a red supergiant orbit with the fate of the real Earth around the real Sun. And we will ask whether any planet could truly be habitable around the largest stars, or whether these giants are better understood as cosmic factories, beautiful for observers far away, but deadly for worlds that get too close. Before we move there, let us pause on one last image. Earth at a safe distance, if such a distance can be called safe. The giant star fills the morning with red light. The oceans are still liquid. Clouds still move. The moon still rises. For a brief era, the planet appears to have survived the impossible. But every instrument pointed at the star says the same thing in different ways. The wind is changing. The outer layers are unstable. The star is losing mass. The future is not fixed. And somewhere deep inside that enormous red body, nuclear burning continues toward an ending no planet can negotiate with. That ending would not begin with a single explosion. Not at first. For a long time, from the surface of Earth, the star might still look almost peaceful. It would rise as a gigantic red-orange presence across the sky. Not a small, bright disk like the sun, but a wide, swollen furnace, with edges that seem less sharp than they should. Its outer atmosphere would be so huge and thin that the boundary between star and space would feel almost blurred. The light would be deep and warm in color, filled with more red and infrared than the sunlight Earth evolved beneath. At the right distance, the ground might still receive a familiar amount of total energy. That is the strange part. If Earth were placed far enough away, the oceans would not need to boil immediately. Air would not have to burn away in the first hour. There could be a zone around even a monstrous star where a planet receives roughly the same energy that Earth receives from the sun. From a simple distance calculation, it sounds almost comfortable. Put the planet far out. Let the light spread. Let the heat weaken. Let the world sit where water can remain liquid. But habitability is not only a number on a chart. It is not just the average energy falling on the top of the atmosphere. It is the kind of light, the stability of that light, the lifetime of the star, the violence of its wind, the chemistry of the planet, the orbit, the magnetic field, the radiation environment, the star's past and the star's future. And that is where the dream begins to fail. Because the biggest stars are not giant, gentle suns, scaled up for larger worlds. They are unstable engines burning through their lives at a speed that makes the history of Earth look impossibly slow. A star like our Sun can remain steady for billions of years. That long stability matters more than we usually notice. It gave Earth time to cool, time for oceans to settle, time for chemistry to become biology, time for single-celled life to transform the atmosphere, time for complex life to appear, time for forests, animals, and eventually minds capable of looking back at the star that powered them. Around the largest stars, time itself is the enemy. A truly massive star can live only a few million years. Even a red supergiant, with an enormous radius, is often a late chapter in the life of a star that has already burned through its easier fuel. By the time it looks most gigantic, the star is not beginning a long, stable era. It is nearing the end of one. If Earth were somehow moved into orbit around such a star after already having life, then the question becomes survival. If Earth had to form there naturally, the question becomes nearly impossible. A rocky planet might form from a disk around a young massive star, but the star would flood its environment with intense radiation, powerful winds, and violent ultraviolet light. The disk could be carved, heated, and blown apart before quiet worlds had time to mature. Even if planets formed, the clock would already be counting down toward disaster. The Sun gave Earth billions of years. A monster star might give a planetary system only millions. That difference is not small. It is the difference between a planet having time to become alive and a planet barely having time to become stable. So imagine our Earth, not born there, but placed there by some impossible act. Imagine it has its oceans, its atmosphere, its continents, its biosphere, and its moon. Imagine it is set into the broad habitable region of the biggest star ever found, far enough away that the first measurements seem survivable. At first, people would look upward and see a sky no human ancestor ever saw. The star would not feel like the sun. It would feel like a world hanging above the world. Depending on the distance and the star chosen, it might appear much larger in the sky than the sun does from Earth, even from hundreds of astronomical units away. Its surface would be cooler than the sun's surface if it were a red supergiant, But the total area of that surface would be so vast that the star would pour out an enormous amount of energy. The result would be a strange contradiction: softer colored light from a far more powerful object. Daylight could become copper-colored. Shadows might be dimmer at the edges because the star's disk would cover a larger patch of sky. Sunrise could be slower and wider, not a point of light climbing over the horizon, but a broad glowing rim flooding the atmosphere in deep orange. Sunsets might stain the sky with colors that make Earth look alien to itself. Plants would face a different spectrum. Earth plants evolved under our sun, using visible light efficiently, especially in certain blue and red wavelengths. Around a cooler red supergiant, much more of the radiation would come as red and infrared light. Some photosynthesis could still work if enough usable visible light reached the surface, but ecosystems would be stressed. Leaves might overheat. Water cycles could shift. Weather patterns might change because infrared interacts differently with air, clouds, and the surface. The planet could be warm and yet not familiar. A human standing outside might not feel burned at first. They might feel a heavy warmth, a strange reddish daylight, and the sky dominated by a star so large that it becomes difficult to look at for emotional reasons, not only physical ones. The first fear would not be instant death. It would be the realization that this new sun is not stable enough to trust. The calendar would change as well. If Earth orbited hundreds of astronomical units from a star many times more massive than the Sun, the year could become thousands of Earth years long. One orbit might outlast civilizations. Seasons, if they came from the planet's tilt, would still cycle annually only in the sense of Earth's own axial motion around its orbit. But the planet's position around the star would change so slowly that the sky would feel almost fixed across human history. Constellations would be different, because we would not be in the same place in the galaxy. The night sky could contain nearby star-forming regions, clouds of gas, clusters, and the surrounding environment where such massive stars are usually born. These stars do not normally live alone in quiet neighborhoods. They form in crowded, violent places, among other young stars. Ultraviolet radiation, dust, and gas sculpted into bright nebulae. The biggest star would not only be a sun, it would be part of a hostile community. Other massive stars nearby could add radiation. Supernova remnants could mark the deaths of older siblings. The sky might glow with nebulae that look beautiful in photographs, but represent an environment far less calm than the region around our sun. This is another hidden problem with placing Earth around. The biggest stars. The star itself is not the only danger. The neighborhood is dangerous too. Our sun lives in a relatively quiet part of the Milky Way. It is not inside a dense star cluster. It is not beside several massive blue stars. It is not being blasted by the strongest radiation fields found in stellar nurseries. This quietness helped Earth. It gave the planet a stable local environment, with fewer nearby stellar catastrophes. A gigantic star usually belongs to a very different setting, and that setting matters. But even if we ignore the neighborhood, even if we isolate the star and give Earth a clean orbit, the star itself begins to change the rules. The first major problem would be mass loss. A red supergiant does not hold its outer layers tightly the way the sun holds its calmer atmosphere. Its surface gravity is weak because the star is so inflated. Its outer gases are spread across a huge volume, and the star can shed material into space in powerful winds. Dust can form in the cooling outer layers. Gas can stream outward. Shells of material can drift away from the star, making the system hazy and unstable. Earth would be orbiting inside a changing environment, not empty space. A slow storm. The solar wind from our sun already affects Earth, but Earth's magnetic field and atmosphere handle most of it. Around a red supergiant, the wind could be far denser. It might move more slowly than the wind from a hot blue star, but it could carry far more mass. Over time, it would fill the system with gas and dust from the dying star's outer layers. A planet in that wind would need protection. Earth's magnetosphere might deflect some charged particles, but the constant flow of stellar material could compress it, reshape it, and erode the upper atmosphere. Auroras could become common and global. The upper atmosphere might expand. Satellites would be dragged, charged, and damaged. Radio communication could be disturbed by plasma effects that never occur around our present sun at the same intensity. And because the star is unstable, the wind would not remain constant. There could be quieter centuries. Then, stronger outflows. Then dusty episodes that dim the light. Then bright phases that increase the energy falling on the planet. A climate system can adapt to cycles if the cycles are moderate and predictable. Earth's climate has survived ice ages, orbital variations, volcanic eruptions, and asteroid impacts. But a massive dying star can change on timescales that are short compared with geological stability, and extreme compared with biological comfort. The planet would be living under a star that is not simply shining, it is shedding itself. This changes the orbit too. When a star loses mass, its gravity weakens. A planet orbiting that star will tend to drift outward over time, because the central mass holding it is decreasing. The effect depends on how quickly the mass is lost compared with the orbital period. If the loss is slow, the orbit expands gently. If the loss is sudden, the orbit can become more eccentric, or the planet can even be thrown free. Around a dying giant, Earth might not stay exactly where it was placed. Its year could lengthen. Its distance could change. The amount of light it receives could shift for two reasons at once. The star's luminosity changes, and the planet's orbit changes. This makes long-term habitability almost impossible to stabilize. Imagine trying to keep Earth comfortable by moving a lamp farther away as the lamp brightens, while the lamp is also losing pieces of itself, changing color, and preparing to explode. That is not a real climate system. That is a temporary negotiation with a collapsing engine. Even if advanced machines tried to manage it, they would face a moving target. Mirrors could reflect light, shades could block radiation, artificial magnetic fields could protect the atmosphere, orbital engineering could move Earth outward. But every solution becomes absurdly large when the star is absurdly large. A sunshade for Earth around our sun would already need to be enormous. Around a red supergiant with hundreds of thousands of times the sun's luminosity, the engineering becomes almost mythological. You are not adjusting a thermostat. You are trying to make a planet safe beside a dying cosmic furnace. And then there is the matter of gravity. A red supergiant may have a huge radius, but its mass is not spread evenly in the way its appearance suggests. The dense core remains deep inside. The outer envelope is extended and tenuous. From far away, the planet feels the total mass, not the surface size. If the star has 20 times the sun's mass, the gravity at a given distance is stronger than the sun's gravity would be at that distance. But because the planet must orbit much farther away to avoid being burned, the gravitational pull can still be moderate. The orbital speed would be different. The year would be different. The stability of moons, satellites, and debris could change. If Earth kept its moon, the moon would still orbit Earth, but the star's distant tides could alter subtle long-term dynamics, depending on the chosen orbit. At hundreds of AU, the star's tide across Earth-Moon distances might be manageable. Closer in, or around an especially massive and luminous object, the system becomes less comfortable. But the real gravitational threat arrives later, when the star dies. Before that final moment, the core is changing rapidly. Inside the star, the outer surface tells only the calmest part of the story. The atmosphere may look red and enormous, but the core is where the clock is measured. Hydrogen burning, has already given way to heavier stages. Helium can fuse into carbon and oxygen. In more massive stars, carbon can burn, then neon, then oxygen, then silicon. Each stage happens faster than the last. A star may spend millions of years burning hydrogen. It may spend hundreds of thousands or less burning helium. Carbon burning can last far shorter. The final silicon burning stage before collapse can last only days. To a civilization on Earth, the star might appear huge and ancient. Inside, it is rushing. The core begins to build elements in layers, like a cosmic onion. Different shells burn different fuels. The center becomes heavier. Eventually, iron group elements accumulate. This is the crucial boundary. Fusion can release energy when lighter elements fuse into heavier ones up to iron. But fusing iron into heavier elements consumes energy instead of releasing it. Iron is not fuel for the star. Iron is the ash that ends the support. A star survives because radiation pressure and thermal pressure push outward, while gravity pulls inward. As long as fusion supplies energy, the star can resist collapse. Once the core becomes iron-rich and massive enough, that support fails. The core collapses catastrophically. Electrons and protons are forced together. Neutrinos burst outward. The outer layers, no longer held in balance, crash inward and rebound in one of the most violent events in the universe. This is the supernova. If Earth is orbiting the biggest star when this happens, distance becomes almost meaningless in the human sense. Even hundreds of AU away, the explosion would not be a bright event in the sky. It would be the sky, becoming an event. The first signal could be neutrinos passing through the planet almost without touching anything. Trillions would move through every human body, through every ocean, through the rock beneath the continents. Most would pass unnoticed because neutrinos barely interact with matter. Detectors would spike before visible catastrophe arrived. Then the light would come. Depending on distance, dust, and explosion type, the supernova could outshine anything Earth has ever seen. It could turn night into a strange, dangerous twilight. The atmosphere would absorb and scatter high-energy radiation. Ozone chemistry could be damaged. Satellites would fail. The upper atmosphere would be ionized. Surface life would face radiation hazards far beyond ordinary sunlight. If Earth were extremely far out, the immediate thermal pulse might not boil the oceans, but the high-energy radiation and particle storm would still be severe. At closer distances, the planet could be sterilized. At very close distances, atmospheres can be stripped, oceans heated, and surfaces transformed beyond recognition. The problem is not only the flash, it is what follows. The supernova ejects material into space at thousands of kilometers per second. Heavy elements forged in the star and during the explosion race outward. Shock waves expand. Dust forms. Magnetic fields twist. Cosmic rays are accelerated. If Earth is in the path, it does not simply watch the star die. It is hit by the star's remains. The blast wave would arrive long after the light, because matter moves slower than photons. For a while, the planet might experience the aftermath as radiation first, then particles, then a changing environment as the expanding debris reaches its orbit. The timing would depend on distance and ejector speed. A world placed hundreds of AU away would have warning after the light, but not meaningful escape without impossible technology. When the ejector arrives, it could compress the magnetosphere, erode the atmosphere, alter chemistry, and deposit exotic isotopes. On a living Earth, this would be more than a bad space weather event. It would be an encounter with the torn open interior of a dead star. And the irony is almost unbearable. The elements that make planets and bodies possible are created by stars. But if you orbit too close to one of the greatest stellar factories, the same process that enriches the universe can destroy the world that witnesses it. This is why the biggest star is not a better sun, It is a temporary creator and a future weapon. If Earth survived the first radiation, survived the particle storm, and somehow kept enough atmosphere to remain a planet with weather, the system would still be changed forever. The central star would be gone. In its place would be a compact remnant. Depending on the original star's mass and the details of its death, the remnant might be a neutron star or a black hole. A neutron star would compress more mass than the Sun into a sphere roughly the size of a city. A black hole would hide its mass behind an event horizon, invisible except through gravity and surrounding matter. For Earth, the difference would matter, but not in the way most people imagine. If the explosion removed a large fraction of the star's mass quickly, Earth's orbit could become unstable. A planet orbits the central mass. Remove too much of that mass suddenly, and the old orbit no longer makes sense. The planet can be flung onto a stretched ellipse or ejected completely into interstellar space. Earth could become a rogue planet. No sunrise, no seasons from a star, only residual heat, radioactive decay, and perhaps whatever atmosphere remained after the catastrophe. If the remnant kept enough mass, and Earth remained bound, the planet would orbit a dead center, not a life-giving star. The sky would contain a small, compact object instead of a swollen red disk. There might be an expanding nebula around it, glowing for thousands of years, a beautiful graveyard made from the star that destroyed the system. A neutron star could be dangerous in a new way. If it formed as a pulsar, beams of radiation might sweep through space like lighthouse beams. If Earth crossed those beams, the surface environment could be blasted periodically with radiation. Even if the beam missed, the remnant would not warm the planet like a normal star. It would not support a green world. It would be a compact ember of physics, not a stable sun. A black hole remnant would not suck Earth in just because it is a black hole. That part is important. If the black hole had the same mass as the remaining star would have had, and if Earth were far away on a stable orbit, the planet could orbit it like any other mass. Black holes are not magical vacuum cleaners. But the problem is that the light is gone. The warmth is gone. The star's stable energy is gone. The planet's biological support has ended. A black hole at the center of the system would be less like a monster chasing Earth and more like an absence that gravity cannot repair. The orbit might continue. Life would not. Unless an advanced civilization had prepared for this outcome, Earth would freeze. The atmosphere would begin losing heat, water vapor would condense, clouds would change, snow and ice would spread. The oceans would freeze from the top down. Deep water might remain liquid for some time under ice, warmed by internal heat, but the surface biosphere would collapse without sunlight. Photosynthesis would fail almost immediately on global biological timescales. Food chains would break, forests would dark, oceans would darken. The world would become a tomb, orbiting a remnant, or a frozen wanderer leaving the system forever. This is the end of the thought experiment if we follow ordinary physics without rescue. The answer is not that Earth would simply burn. That is only the simplest version. The fuller answer is stranger. At the wrong distance, Earth is swallowed by the star's extended atmosphere or vaporized by heat. At a safer distance, Earth may receive enough energy for liquid water, but it lives under a star too unstable and short-lived for lasting habitability. At the end, the star's death either sterilizes the planet, strips it, ejects it, or leaves it orbiting a dead remnant. The best case is temporary survival. The worst case is immediate destruction. The realistic case is a planet that can look alive for a while, but never truly belongs there. And that is perhaps more unsettling than an instant catastrophe. A world can be placed in the right temperature zone and still be doomed. It can have oceans and still have no future. It can orbit under beautiful red light, while its star is already preparing the event that will end everything. This separates a habitable location from a habitable history. Earth is not alive only because it sits at a certain distance from the sun. Earth is alive because it has occupied a stable relationship with the sun across immense time. The distance mattered, but so did the sun's patience, so did its moderate mass, so did its long main sequence life, so did the fact that it is not too violent, not too short-lived, and not already swollen into its final crisis. Around the biggest star ever found, the location might be adjusted. The history cannot. That is why the question becomes terrifying, because it reveals something hidden about our own world. The sun is not impressive because it is the biggest. It is impressive because it is stable. In a universe filled with stars that outshine it, outweigh it, and dwarf it in size, the sun is ordinary in exactly the way life needed. It burns slowly, it changes gradually, it gives planets time. It is not too bright, not too dim, not too massive, not too young, not too close to death. A gigantic star may dominate a telescope image. A moderate star can build a biosphere. That difference is everything. So, if Earth orbited the biggest star ever found, the first chapter might look magnificent. The sky could glow with a vast red sun. The scale would be almost impossible to accept. Every sunrise would remind the planet that it now circles something far beyond the sun in size. But the deeper story would not be wonder. It would be instability. The planet would have to sit far away to avoid being destroyed by the star's luminosity. Its year could stretch across millennia. Its daylight would shift in color and character. Its atmosphere would face stronger winds and changing radiation. Its climate would depend on a star that is losing mass, changing brightness, and approaching a violent end. And if life survived the light, it would still have to survive the clock. That clock would be unforgiving. A giant star does not offer deep time. It spends itself quickly. It becomes spectacular because it is burning through possibility at a rate ordinary stars avoid. For a human observer, that spectacle is beautiful. For a planet trying to remain alive, it is a warning. The greatest stars are not homes. They are events. They happen to the galaxy. They sculpt nebulae, forge elements, trigger new waves of star formation, and explode their interiors into space. They help make future worlds possible. But the worlds too close to them pay the price for being near the furnace while it operates. A planet like Earth needs more than energy. It needs mercy from time. It needs a star that can wait. The biggest star cannot wait. There is another version of the thought experiment, and it is even harsher because it removes the comfortable adjustment we made earlier. What if Earth did not get moved to the safe distance? What if Earth simply stayed where it is now, one astronomical unit from the center of the star? Around the Sun, that distance feels natural because it is the orbit Earth has always known. Around an enormous red supergiant, that same distance would be meaningless. Many of the largest red supergiants have radii far larger than Earth's orbit around the Sun. Some estimates for the most inflated candidates are so large that their outer layers would extend beyond the orbit of Mars, Jupiter, or even farther, depending on the star and the measurement used. That means Earth would not be orbiting beside the star. Earth would be inside it, not inside a solid surface, because stars do not have solid surfaces like planets, but inside the extended outer atmosphere, inside a vast region of hot, thin gas belonging to the star itself. The sky would not show a red sun overhead. The sky would be star material in every direction. The atmosphere would be crushed and heated. The oceans would not last. The surface would be exposed to gas, radiation, drag, and heat beyond anything Earth can handle. A planet moving through the outer envelope of a giant star would lose orbital energy. Drag would slow it down. Instead of circling peacefully, it would spiral inward. The process would dump energy into the star's outer layers, disturb the gas around it, and gradually erase the planet as a separate world. Earth's crust would melt, rock would vaporize, the atmosphere would be stripped and mixed into stellar gas. The moon would be dragged into the same catastrophe, or torn away by the changing gravitational environment. At one astronomical unit, the question would not be how long life survives. It would be whether Earth remains recognizable for more than a short physical episode. This is why scale comparisons can be misleading. A star can be so large that ordinary planetary distances disappear inside it. If you placed a star like that where the Sun is, the inner solar system would not simply be warmer, it would be engulfed. Mercury would vanish, Venus would vanish, Earth would vanish. Mars might not be safe either, depending on the chosen star's radius. The asteroid belt, Jupiter, and beyond become the places where planets might still orbit outside the star's visible body. But even there, the radiation and mass loss would reshape everything. So the only meaningful survival scenario requires moving Earth far outward. That sounds like cheating, but it is necessary if the question is about orbiting rather than being consumed. Once Earth is moved outward, a different kind of danger appears: distance itself. At hundreds or thousands of astronomical units, the star can provide enough energy because it is so luminous. Yet the planet is no longer in a compact solar system like ours. It is far from the central object, with a huge orbital path and a weak connection compared with Earth's current orbit. The orbit could become vulnerable to passing stars, nearby cluster members, and gravitational nudges from the environment where massive stars often live. Our Earth is about 1 AU from the Sun. Neptune is about 30 AU from the Sun. A habitable orbit around a truly luminous supergiant could be far beyond Neptune's distance. In some versions, it could sit hundreds of AU out. In more extreme luminosity cases, it could be pushed still farther. Now imagine Earth there. The Sun's familiar solar system would fit deep inside the orbit. The planet would circle so far out that, in our own system, it might be in a region associated with distant icy bodies rather than a warm blue world. Around the monster star, however, that far place could still receive enough light to keep water liquid. This creates one of the most haunting images in the whole thought experiment. Earth becomes a habitable world at a distance where, around our Sun, it would be frozen almost beyond recognition. The star is so bright that it moves the warm zone outward into regions that normally belong to darkness. But that warmth is borrowed from instability. The planet's year becomes extremely long. If Earth orbited hundreds of AU from a star with many solar masses, one revolution could take thousands of years. If it orbited even farther, the year could become longer than recorded human history. This would make astronomy feel different. Civilizations might live and die without seeing the planet complete a meaningful fraction of its orbit. Ancient monuments would not mark the return of seasons around the star in the way our calendars do. The star would move against the background more slowly. The deep orbital story would be almost invisible to daily life. A human lifetime would become a tiny measurement inside a single year. Yet day and night would still depend on Earth's rotation. If Earth kept a 24-hour spin, people would still see the huge star rise and set. But the rhythm of the sky would feel disconnected from the planet's slow journey around the star. The day would be familiar. The year would become nearly mythological. This could have strange climate effects. On Earth today, seasons are caused mostly by axial tilt, not distance from the Sun. If Earth kept its tilt, seasons would still occur as different hemispheres lean toward and away from the light. But the planet's position around a very long orbit would change, so slowly that orbital seasons would stretch into deep time. If the orbit were eccentric, the difference between nearest and farthest parts of the path could matter. But the cycle might be longer than civilizations. A society living there would know that the planet is moving through a gigantic orbit, but almost no one would experience the full cycle. The star itself would change faster than the orbit. That is the disturbing reversal. Around the Sun, Earth's year is short, and the Sun changes slowly. Around the biggest star, Earth's year might be long, and the star changes quickly. The planet would not circle a clock. It would circle a countdown. Another scenario is worth separating from the red supergiant version. Because when people say the biggest star ever found, they can mean different things. The largest star by radius is not necessarily the most massive star. A red supergiant may be physically enormous, with outer layers spread across space, but it may not be the heaviest star known. A very massive blue or Wolf-Rayet-like star can be far more massive and luminous while having a smaller radius compared with an inflated red supergiant. If Earth orbited the most massive or most luminous star instead of the largest by radius, the danger changes shape. The star may not swallow Earth's 1 AU orbit by size. It may destroy Earth through radiation instead. Hot, massive stars pour out intense ultraviolet light. Their surfaces can be far hotter than the Sun's. Their light is not soft and red. It is blue-white, harsh, and energetic. They can ionize gas across enormous distances. They carve bubbles in nebulae. They drive fierce winds. They flood their surroundings with radiation capable of breaking molecular bonds and stripping atmospheres. To receive Earth-like total energy from a star millions of times brighter than the Sun, Earth would need to be placed extremely far away. But total energy is still not the whole story. The spectrum would be hostile. Even if the planet's average temperature were adjusted into a liquid water range, the ultraviolet environment could be severe. The upper atmosphere would need to absorb enormous amounts of high-energy radiation. Ozone, chemistry, and magnetic shielding would become matters of survival. Life on the surface might be impossible without a thick protective atmosphere, deep oceans, caves, or artificial shielding. The sky would not be copper. It could be brilliant and pale, with a star so hot that looking at it would feel less like seeing a sun and more like facing a welding arc spread across a huge distance. Around such a star, photosynthesis might receive plenty of visible light, but the same star could damage DNA, erode atmospheres, and sterilize exposed surfaces. The habitable zone would be wide and distant, but it would not be gentle. And the lifetime problem becomes worse. The most massive stars live the shortest lives. They are cosmic fireworks, not long-burning hearths. A planet around them would be living near something that can produce tremendous energy only because it is spending fuel at a catastrophic rate. It may influence its birth cloud, shape future star formation, and forge heavy elements in its death. But as a host for complex life, it is almost the opposite of ideal. So the title hides two different nightmares. If the biggest star means the largest radius, Earth must move far away or be swallowed, then survive a dying red supergiant. If the biggest star means the most massive or luminous, Earth must survive brutal radiation, fierce winds, and a star that may die before biology can become complex. In both cases, the biggest star is a poor home, for different reasons. There is also a quieter issue that makes this thought experiment feel less like science fiction and more like a warning about selection bias. We tend to notice extremes: the largest star, the hottest planet, the fastest wind, the brightest explosion. Extreme objects make good titles because they stretch imagination. They are easy to picture as records. They feel important because they are rare. But life may not prefer records. Life may prefer boring stability. The largest star ever found is fascinating because it pushes the limits of stellar physics. It tests how stars hold themselves together, how radiation pressure fights gravity, how mass loss works, how dust forms, how stellar atmospheres become extended and unstable. For astronomy, it is a treasure. For Earth, It is a terrible landlord. A habitable planet needs ordinary miracles. A star that does not change too quickly. A radiation environment that does not erase chemistry. A lifespan long enough for slow processes. A gravitational environment calm enough for planets to remain in steady orbits. A planetary system not constantly disrupted by nearby stellar giants. These qualities do not make headlines the way enormous size does. But they make biology possible. This is why the Sun becomes more impressive after we compare it with monsters. At first, the Sun may seem small. It is not the largest. It is not rare in the way record-breaking stars are rare. It is one of many yellowish main sequence stars scattered through the galaxy. But its moderation is not a weakness. It is the exact feature that allowed Earth to become a planet with memory. The Sun has been brightening slowly, not violently. Its output changes, but gradually. Its magnetic storms can be dangerous, but they are not the constant atmosphere-stripping winds of a massive stellar monster. Its lifetime is long enough for oceans, oxygen, evolution, and intelligence. The biggest star ever found can make the Sun look unimpressive in a size chart. But the Sun wins in the category that matters to life. It lasts. If Earth orbited the biggest star, one of the hardest things for humans would be psychological. The sky would be magnificent, but every educated person would know the truth behind it. Every sunrise would be a reminder that the star was too large to trust. Every observatory report about mass loss or brightness change would feel like a weather forecast for the end of the world. Children might grow up under a red giant sky and think it normal. Farmers might learn the new light. Engineers might build power systems around the different spectrum. Astronomers might track the swelling, pulsing surface. Governments might plan for stellar variability the way modern societies plan for climate risk, asteroid impacts, or solar storms. But the scale would be too large for ordinary politics. No treaty can calm a supergiant core. No technology can make a massive star burn hydrogen slowly again once it has left that stage. No civilization can negotiate with iron. The planet would live in the shadow of astrophysics. That phrase sounds poetic, but it is literal. The fate of the biosphere would be controlled by processes deep inside a star whose core no one could reach, alter, or slow. Fusion stages would proceed. Mass loss would continue. The envelope would shift. The final structure would form. Collapse, eruption, or remnant formation would arrive when stellar physics allowed it. Human history would become a footnote inside stellar evolution. And this is where the thought experiment becomes most useful. It does not only ask whether Earth could survive around a huge star, it asks what kind of universe permits survival at all. Most places are not like Earth. Most stars are not like the Sun. Most orbits are not comfortable. Most cosmic environments do not provide long, quiet windows for life to think about them. A record-breaking star is impressive, but it shows how narrow our good fortune may be. The universe is full of energy, but energy alone does not make a home. Too much energy destroys. Too little freezes. Energy arriving in the wrong form poisons. Energy changing too quickly destabilizes. Energy from a short-lived star runs out before complexity can build. The right amount must arrive in the right way, for the right length of time. That is a much stricter condition. Earth did not simply need a star. It needed this kind of star. Not exactly unique, but not arbitrary either. There are many stable stars in the galaxy, and some may host worlds far more suitable for life than we know. But the biggest star ever found would not be one of the first places to look for an Earth-like future. It is too massive, too unstable, too short-lived, too violent, or too late in its life, depending on which record holder we choose. Its greatness belongs to astronomy, not habitability. Now, imagine one final view. Earth has been moved outward. The oceans still exist. Humans have had generations to adapt. Cities are shielded. Agriculture has changed. The night sky contains nebulae and clusters. The day sky glows under a star that looks less like the sun and more like a looming red horizon suspended above the world. For centuries, the planet survives, maybe longer. Civilization learns the star's rhythm. It maps surface cells larger than Earth's orbit around the sun. It watches immense convection patterns rise and fade. It studies dust shells drifting outward. It records changes in spectral lines that reveal the star's outer layers escaping into space. Then the warnings sharpen. The star dims unexpectedly, then brightens, then loses another shell of material. Neutrino detectors buried deep underground begin to show changes that ordinary citizens do not understand at first. Astronomers speak carefully. Governments avoid panic. The star still rises, the sea still reflects it, but the equations have stopped being comforting. At that point, even the most beautiful sunrise becomes a countdown display. The last human generation under that star might not see the explosion coming with their eyes until it is too late. Or they might know for years that the internal stages are nearly finished. Either way, the end would not feel like weather. It would feel like living beside a mountain that is also a bomb, except the mountain is larger than the solar system, and the bomb is stellar collapse. If escape were possible, the civilization would have to leave not just the planet, but the system. Moving to another orbit would not be enough. No safe distance nearby would preserve an Earth-like world through the full aftermath, unless the technology were extraordinary. Habitats might flee into interstellar space. Ships might depart long before the final event. Archives might be launched. The planet itself, too massive and too bound to its history, would likely remain. In that version, Earth becomes the cradle that cannot be saved. A world carried into the wrong stellar story, and the biggest star becomes not only a source of light, but a deadline for civilization. This adds a final answer to the original question. If Earth orbited the biggest star ever found, humanity's survival would depend less on standing on Earth and more on knowing when to leave it. That is a dark reversal of our normal hopes. Around the sun, we imagine protecting Earth. Around a monster star, protection may eventually mean evacuation. A living planet can be kept warm, shielded, repaired, and managed for a while. But it cannot remain a permanent home when the central star is entering the final crisis of massive star evolution. The planet may survive physically in some altered form, but the biosphere would not survive indefinitely without intervention. And even intervention has limits. The star's scale makes every solution expensive in energy, materials, time, and coordination. You can build underground cities, but not underground photosynthesis without power. You can build orbital shields, but they must survive dust, radiation, and changing luminosity. You can move populations, but only if you have somewhere to go. You can preserve data, but data is not a living ocean. The biggest star forces a civilization to confront the difference between saving life and saving Earth. Those are not always the same task. Under our sun, they feel linked. Under a dying supergiant, they separate. Perhaps the only truly successful civilization in that system would be one that never trusted the planet as permanent. It would build ships early. It would spread through artificial habitats. It would treat Earth as a temporary garden under a doomed light. That sounds tragic, but it may also be the only reason anyone survives the star's end. In this way, the biggest star turns habitability into a lesson about humility. A planet can be beautiful, wet, and alive, yet still be temporary because the star above it is temporary in the wrong way. It is not enough to ask whether a world has water today. We must ask what its star will do tomorrow, and whether tomorrow lasts long enough to matter. For Earth, tomorrow around the sun stretches across billions of years before the worst changes arrive. Around the biggest star, tomorrow may be far shorter. That is the hidden horror beneath the magnificent scale. Not that the star is large, but that its largeness is a symptom of an unstable chapter. There is one more way to measure the danger, not by asking whether Earth survives the first day, not by asking whether the oceans can remain liquid at one carefully chosen distance, but by asking how many layers of survival have to line up at once. The first layer is thermal survival. Can the planet receive the right amount of energy to avoid freezing or boiling? With enough distance, the answer can be yes for a while. A star that is hundreds of thousands of times more luminous than the sun can warm a planet from far across space. The math can be adjusted. Move Earth outward until the average energy looks familiar. But the second layer is atmospheric survival. Can the planet keep its air under stronger stellar winds, changing radiation, and possible high-energy events? That answer is less comforting. Earth's atmosphere is not just a blanket. It is a chemical system. It depends on temperature, ultraviolet light, magnetic protection, volcanic recycling, oceans, and life. Change the star too much, and the same atmosphere that works here may become unstable there. The third layer is biological survival. Can living systems handle the new spectrum, the radiation bursts, the changing climate, and the stress of a star that may dim, brighten, pulse, or shed material? Some microbes could hide underground or underwater. Humans would need technology. Surface ecosystems would face the hardest test because they are directly tied to light, temperature, and atmospheric chemistry. The fourth layer is orbital survival. Can the planet keep a stable path as the star loses mass and the local environment changes? This depends on timing. Slow mass loss can expand an orbit. Sudden mass loss can destabilize it. A supernova can rewrite the system in a single event. The planet's path is not guaranteed simply because it begins in the right place. The fifth layer is historical survival. Does the star last long enough for the planet's story to matter? This is the layer people forget. A world can have a tolerable climate for 10,000 years and still be a terrible home for life if the star dies before ecosystems can recover from major changes. Earth needed long stretches of stability after disasters. It needed time after impacts, ice ages, volcanic crises, and atmospheric transformations. A giant star does not offer that kind of patience. When all 5 layers are considered together, the answer becomes clearer. Earth might survive around the biggest star as an object. It might survive as a warm planet for a limited era. It might even carry human life for some time, if placed carefully and protected by technology. But it would struggle to survive as Earth in the deeper sense. Earth is not just a rock with water. It is a long-running balance, a relationship between star, atmosphere, ocean, crust, magnetic field, moon, chemistry, and biology, held together across billions of years. The biggest star would break too many parts of that relationship too quickly. This is why the thought experiment feels so powerful for a space documentary. It begins with a simple visual: Earth under the biggest star. But it ends by showing that size is not the same as suitability. The universe often gives us spectacular things that would be terrible to live beside. A black hole can be beautiful in simulations. A supernova can seed future planets with heavy elements. A nebula can glow with colors that look peaceful through a telescope. A red supergiant can make the sun look tiny. Yet beauty from far away is not safety up close. Many of the most stunning objects in astronomy are stunning because they are violent, unstable, energetic, or dying. A planet does not need spectacle. It needs restraint. And restraint is exactly what the biggest stars do not have. If a person on that altered Earth looked at the star each evening, They might feel something different from fear at first. They might feel awe. The star would be so large that the mind would struggle to place it in ordinary categories. It would make mountains look small. It would make the moon feel fragile. It would make the old sun seem like a memory from a quieter universe. But after enough time, awe would become knowledge. Knowledge would become planning. Planning would become dread, because every measurement would point in the same direction. The star is not a permanent ceiling over the world. It is a phase. And living under a phase is different from living under a star with billions of calm years ahead. This is the uncomfortable truth behind all extreme star habitability. Even if the present moment can be engineered into comfort, the future cannot be ignored. A civilization could build domes, satellites, shields, underground oceans of data, and fleets of escape craft. But those are not signs that the star is safe. They are signs that the star is forcing life to become temporary, mobile, and defensive. The biggest star would not invite Earth to settle. It would force Earth to prepare. And if no one prepared, the planet would eventually learn the difference between orbiting a sun and orbiting a countdown. That is why the question is not only about astronomy, it is about the fragile kind of luck hidden inside ordinary daylight. We live under a star that is powerful enough to warm a planet, but restrained enough not to end the experiment too quickly. That balance is easy to overlook until we imagine losing it. And that is the final answer to the question. If Earth orbited the biggest star ever found, it might survive for a while if it were placed far enough away. It might keep oceans under a strange sky. It might have copper days, enormous sunrises, altered weather, and a year longer than recorded civilization. But it would not have the long, quiet future Earth has enjoyed around the sun. Eventually, the star would change. Eventually, its wind would grow heavier. Eventually, its core would reach the stages that cannot be slowed. Eventually, the sky would announce the death of the thing that had been keeping the planet warm. And after that, Earth would either be burned, broken, stripped, frozen, thrown away, or left circling a remnant that no longer knows how to be a sun. The greatest star would make Earth feel smaller than ever, not because of size alone, but because size in stars often means speed. It means pressure. It means instability. It means a life too bright to last. The sun, by comparison, is not a cosmic champion. It is not the largest star, the hottest star, the brightest star, or the most dramatic. It is a middle-aged yellow star in a quiet region of one galaxy among billions. And yet, that may be exactly why we are here, not because our star is extreme, but because it is not. The biggest star ever found may be more impressive than the sun in every obvious way. But Earth does not need impressive. Earth needs steady. It needs time enough for rain to carve valleys, continents to drift, microbes to alter air, forests to rise, animals to move, and minds to ask what would happen if all of this were placed beside a star too enormous to last. The answer is that Earth would be standing beside beauty with no promise. A world under a giant light, a living planet near a dying engine, a familiar home in the wrong story. And eventually, when the final change came, the size that made the star famous would become the reason no orbit could save us. Because in the end, the biggest star does not simply shine over its planets, it decides how their story ends.